Hi everyone. The official title of this lesson is Implicit Differentiation. I hate that title because it makes it sound like this is something new, and it's really not new. A better title is Stealth Chain Rule. Because what you'll see is that implicit differentiation is just the chain rule, but stealth. Every time we've been working with functions, like a function f of x, what we've been saying is that it's like a machine into which you put an x value and out of which comes a y value. So we could have been saying all this time that y equals f of x, or the y value is equal to the number that comes out of f of x. We've kind of already been doing this. We've had questions where f of x is given as f of x equals stuff in terms of x, and we've had functions given as y equals stuff in terms of x. If you're asked for the derivative, you could be asked for f prime, or you could be asked for y prime, and it means the same thing. So for a very simple example, if our function was described as y equals 4x squared plus 6x plus 8, the derivative would be y prime, which we would compute using the power rule as 8x plus 6, or 8x plus 6 plus 0, since the derivative of 8 is 0. And then we can just drop the plus 0 since it doesn't have any effect on the answer. Those functions are called explicit functions of x. And we contrast them with implicit functions of x, like the one that's shown here. What makes a function implicit is a mixture of x's and y's that cannot be easily disentangled. So for example, if I was to ask you to isolate for y inside this formula, get y equals stuff in terms of x, even if it was possible, and I'm not even sure, I haven't tried, I don't think it is, but go ahead and give it a shot. But even if it is possible, it's not necessary. If all you're asked for is to find y prime, there is no need to get y all by itself. There's another way you can do it. And it's not even a new rule. It's old rules used in a different way. I'm going to show you what that different way is with a maybe complicated or maybe less complicated, but it is truly less complicated looking example. Y to the 4 equals 4x to the 2 plus 6x plus 8. And what we're asked for inside this example is to find y prime. What we have to do is we have to pay attention to the difference between pieces of the expression corresponding to variables and pieces of the expression corresponding to functions. Y is a function. X is a variable. X here occurs in two different locations. I'll just be careful to label that. And remember what we did in the chain rule when we were taking the derivative of a function to a power. Y to the power 4 is like x squared plus 1 to the power of 4. And how did we take that derivative? Why did I dot the L instead of the I? Okay, so why did we take, or how did we take that derivative? Well, we said this is w to the power 4. So the derivative take the derivative, we get 4 w to the 3 times w prime. Or if we don't want to use w, we could leave the y the way it is. We get 4 y to the 3 times y prime, just using a different label of the alphabet. Also representing a function. What we will do is we will take the derivative of both sides of this expression using the chain rule on the left-hand side. D by dx of both sides. Use the chain rule for any part involving y. So let's take the derivative using this chain rule. The derivative of y to the power 4, y is a function. It's like w to the power 4. The 4 will come down. Y to the power of 3 times y prime. Now on the right hand side we have 8x plus 6 plus 0. Plus 0 doesn't change anything. The question was to find y prime. Next, we isolate for y prime. So we get y prime is equal to 8x plus 6 divided by 4y to the power of 3. And that is the answer. We didn't need any new tools. We had all the tools that were necessary. We just had to identify that y to the power 4 is just like w to the power 4. And every time we did a chain rule of that form, old power comes down, new power gets reduced by 1, multiplied by a derivative of the inside. We were kind of getting ready for this. We were getting ready for taking derivatives of implicitly defined functions. So to remind you about the chain rule, how do you take the derivative of 3x to the 4 plus 2x plus 1 all to the power of 3? Just a quick refresher, even though you may have just looked at the video. First, I call everything in the brackets w, where w is equal to 3x to the 4 plus 2x plus 1. Then the derivative, f prime of x, will be 3w squared times w prime, and now we'll substitute in the pieces. 3 times 3x to the 4 plus 2x plus 1 all to the power of 2 multiplied by w prime. So when we take the derivative of that, we'll get 12x to the 3 plus 2 using the power rule. Likewise, the derivative d by dx of y to the power of 3 is going to be 3y to the 2 multiplied by y prime. So there's a nice, I don't want to call it symmetry, but there's a nice similarity. We're just using a different letter of the alphabet for this implicit differentiation. We're using y instead of a w. Same idea. Check. Just had to check the microphone there. All right. Next example, we want to find y prime, keeping in mind that y is a function and x is a variable. Y is a function, x is a variable. So we take the derivative of both sides. I keep writing this d by dx thing. It means take the derivative. I should make that a little bit neater though. Okay, we use the chain rule on the left-hand side. We'll use it not because it's on the left-hand side, but because that's the piece that contains a function of y. The 2 comes down. We have y to the power of 1 multiplied by y prime. Right-hand side, derivative of x squared is 2x, and derivative of 2 is 0. We don't need to write y to the power of 1. We can just write it as y. So 2y, y prime is equal to 2x. The goal is to get y prime all by itself. I'm going to divide both sides by 2y. And then we can simplify, cancel the 2's. This is just x over y. Normally, either this example or one of the next examples, a hand would go up and someone would ask, do I need to get my final answer completely in terms of x? And the answer is no. The final answer can be in terms of x and y. What cannot happen, if you want a correct final answer, you can't have y prime equals, and then on the right-hand side, stuff with x, y, and y prime. to get a proper final answer, y prime always has to be all by itself. And in the last two examples, that didn't really come into play. It wasn't an issue, it wasn't a problem, but you'll see that sometimes it is. So our general recipe for taking an implicit derivative. Look for a function that cannot easily be isolated for y in terms of x. Even if you can do it. Do some weird completing the square stuff and do plus or minus square roots. Don't bother trying. If it's not already y in terms of x, it's meant to be an implicit derivative. So identify a situation where you're supposed to take an implicit derivative, then take the derivative of both sides of the expression. You'll have to use the chain rule on any function of y. You may need product rules. You may need quotient rules. You may need other derivative laws in addition to the chain used on the parts for y. Then you may have a giant mess. And this last step, step 3, is often the hard part, to get y prime all by itself. Because if y prime is going to appear in multiple spots after you take those derivatives, you're going to have to do some rearranging. And lots of mistakes can happen in that process. So here's one such example where we're going to have two instances of y prime appear. We're going to have to deal with that. Y is a variable. Another question that often comes up at this point is, how do you know y is the variable? The fact that it's asking us for y prime, or the fact that it's asking us for dy by dx, means that we're treating y as, what am I saying? Y is a function. We're treating y as a function. Did I write variable elsewhere? Function, good. Okay, I just screwed up that one. Thankfully, y is a function. How do we know it's a function instead of a variable? Well, it's telling us to take the derivative of y with respect to x. So think about the definition of the derivative. Limit as h approaches 0 of f of x plus h, or y of x plus h minus f of x all over h. We're making a small change in x, so we're varying the x coordinate when we take the derivative with respect to x. So that's the variable. The thing that we're not explicitly varying is y. It's a function of the thing that we are varying. Legos all over the floor. I wonder how that happened. Okay, so the next thing I'm going to do is I'm going to take the derivative of both sides. Using chain rules when needed. So that would be for the y to the 4 and y to the 3. We need chain rules for those because that's a function to a power. So when we differentiate y to the power of 4, we get 4y to the 3 times y prime. Derivative of x to the 4, since x is a variable, not a function, is just 4x to the power of 3. There's no multiplication by x prime. But if you want to, you can say times x prime. What is x prime? It's the derivative of x with respect to x. So what's the derivative of 3 times x? 3. What's the derivative of 7 times x? 7. What's the derivative of 1 times x? 1. So you could write times x prime, but x prime is always going to be 1. It's not necessary to write x prime. Okay, next piece, the derivative of y to the 3 is 3y to the 2 times y prime. On the right-hand side, now we have the derivative of 1 times x, which is 1, and the derivative of 5, which is 0. Next step is we want to get y prime all by itself. What I recommend every time you do one of these is to keep all the pieces with y prime on the left-hand side and move any pieces that don't contain y prime, move them to the right. So the 4x to the power of 3 does not contain any y prime. I'm going to move it to the right-hand side. I'm going to subtract it for both sides. The one that's already on the right-hand side, I'm going to leave it there because it does not contain y prime. So we're going to have 4y to the 3, y prime, minus 3y to the 2, y prime, is equal to 1 minus 4x to the power of 3. common factor y prime. We can common factor out more than y prime on the left-hand side, but it's not necessary. Just common factor out the y prime. So I common factor out y prime, and the first part I'm left with 4y to the 3, and the second part I'm left with 3y to the 2. On the right-hand side, nothing changes because I didn't have to factor anything there. I just factored on the left. And now we're actually almost done. We have y prime, the thing that we're after, the target of our desires, multiplied by stuff that we don't want with it. It's interfering. Get it out of the way. How do we get it out of there? Well, we divide both sides by that bracket. We bring the 4y cubed minus 3y squared, we bring it down underneath on the right-hand side. So divide both sides by that, and we get y prime is equal to 1 minus 4x to the power of 3, all divided by 4y to the 3 minus 3y to the 2. That's our answer. So that's substantially more challenging than the last one because of all those steps we needed to get through to isolate for y prime. Lots of places where mistakes can happen. All right, we'll go through the next set of examples, being careful to follow all the rules that we need to follow. In every case, y is a function, x is a variable. So when we take the derivative, which I'll again denote by d by dx, we get 2x plus 2y to the 1 times y prime. This is y to the power of 2. The 2 comes down. The new power on y is 1, multiplied by y prime, equals 0. Now, I'm going to subtract 2x from both sides. So 2y prime is equal to negative 2x. Then divide both sides by 2y. So negative 2x divided by 2y, which is negative x divided by y. Take a moment to mention something here. In future calculus courses, including Math 1225, Math 1230, and second year calculus courses, so if you do the Calculus 1000, 1301 stream after this course, and then you do second year calculus after those, you'll come to a point where y is no longer treated necessarily as a function. It can be treated as a variable. You can have an x variable and a y variable, two variables input into one function. It's called a multivariable function. And it's very different than what we're doing here. We no longer have just derivatives, we have what are called partial derivatives. So I don't want you to get confused if you're looking at resources online, if you're looking for derivatives with y. If you see anything about partial derivatives, ignore that. That's not inside this course. That's inside the next, somewhere in the next part of the sequence of calculus. We only do single variable functions inside Math 0110. Anyway, it has nothing to do with these problems. I just thought about it because just random thought popped in. Intrusive math thoughts. Okay, next one down below. We'll do the same thing. We'll take the derivative of all the pieces, d by dx, using the chain rule or implicit differentiation everywhere it applies. The first part, derivative of x to the power of 3 is 3x to the power of 2. The second part, derivative of y to the 3 is 3y to the 2, multiplied by y prime because y is a function. On the right-hand side, the derivative of 5x is 5. Y prime was, again, only appearing in one spot, but we have some work to do anyway. We have to isolate for it using a few moves. One of those moves is to get rid of any piece that does not contain y prime, move it over to the other side. So I'm going to subtract 3x squared from both sides. And now we're almost done. We just have to divide by the 3y squared that's interfering with the y prime. So y prime is equal to 5 minus 3x squared divided by 3y squared. That's our answer. Okay, the next example, we have mixed expression of x's and y's. So this is an implicit derivative. We're going to take the derivative of both sides. And by the way, we always take the derivative of both sides, even for explicit functions. It's just, if the left-hand side is f of x, and the derivative of f of x is just f prime of x. It's something we always do, but now we have to pay extra close attention to it. Okay, derivative of x to the power of 3 is 3x squared. Derivative of y to the 3 is 3y squared y prime. And then on the right-hand side, we have a y expression happening again, so we need to chain rule a second time. The 2 is going to come down multiplied by the 5, so we'll have 10 times y to the power of 1 multiplied by y prime. Now, some caution. Y prime is appearing in both spots, and there are two legitimate ways to proceed. One way is to move the 3y squared y prime over to the right-hand side and subtract from both sides. That's smarter, but I'm not going to do it. I'm going to be extremely consistent with what I've shown you so far. I'm going to subtract 3x squared from both sides. 3y squared y prime is equal to 10y y prime minus 3x squared. And then I'm going to subtract 10y y prime from both sides. So 3y squared y prime is equals minus 10y y prime is equal to negative 3x squared. I just trying to be very consistent, always bringing the y prime stuff to one side, always to the left side. Mathematically, there's no difference between the left-hand side and the right-hand side. You can interchange them. You can change the order in which they're written. But I think it's helpful if I don't do that. It's helpful if I always consistently show you moving stuff to the left-hand side. Next step, I'm going to common factor the y prime from the left. So y prime times 3y squared minus 10y is equal to minus 3x squared. You're about to hear some screaming of a toddler. I think he's found me. Minus 3x squared divided by, now divide both sides by 3y squared minus 10y. And that's our answer. Now, I'm getting questions about the homework, which is great. Like, how come this is happening? How come that is happening? And I'm going to get a question about this. Or, if you had have done what I said is smarter, if you had have, at the very beginning, after taking the derivative, subtracted 3y squared y prime from both sides, and the answer that you will find looks a little bit different than this, but it's equivalent. You would find y equals positive 3x squared divided by 10y minus 3y squared. The relationship between these two is that if you multiply by 1 using a fancy form of 1 that's equal to minus 1 divided by minus 1, you'll be able to switch from the one that's circled to the one that's below it. You'll have to also change the order of addition, but that's also a trivial step. Just a warning, if you're checking your answers in the back of the book, you may have to do this. You may have to think, oh yeah, that's that thing he mentioned in the video where, I have a choice and move everything to the right, move everything to the left. It's just because it moved everything to the left and the textbook moved everything to the right, and it's arbitrary, and there's nothing I can do about that. Someone's going to be upset no matter which way it's written, depending on which side they move theirs to and which side I move mine to. All right, now we get into the hard ones. What makes these hard? What makes these extra challenging? What makes them extra challenging is you have to pay more attention. Thinking about the rules that are present. What type of derivative laws are there? You see a mixture of x's and y's. So you think, okay, y to the power of 2, definitely implicit differentiation. What you might miss is the fact that there's a product rule inside this first example, where the first part of the product, a, is equal to x squared, and the second part is equal to y squared. So a prime is equal to 2x. B is equal to y squared. What's b prime? B prime is 2 times y to the 1 times y prime, and we don't bother writing the power 1. Okay, so we'll take the derivative, acknowledging that there is a product rule for this derivative. So on the left-hand side, we'll get ab prime plus ba prime. On the right-hand side, we have 5 plus 0. Derivative of 5x is 5. Derivative of 5 all by itself, not multiplied by a function, is just 0. Now I'm going to plug in the a prime, b, and b prime. So x squared times b prime, 2y, y prime, plus b, y squared times a prime, 2x, equals 5. So I'm going to rewrite this in standard form. Standard form means those of you in Math 1229, standard form means something else, but for functions, standard form means constants go in front, x terms go next, and then y terms go after that, and if we had z terms, they would go after the y terms. So the 2 goes in front, then the x squared. Now I'm going to put the y before the y prime, which is also standard. For the second piece, I'm going to put the 2 in front, the x after, and the y squared after that equals 5. That's truly not important, but I'm going to make it match what the appearance would be on a test or a quiz or inside the textbook. Could be written in that order. Okay, now we don't have multiple pieces with y prime. We only have one piece with y prime, but we do have a piece on the left-hand side that does not contain y prime. So we have to do a subtraction. We've got to bring it over. 2x squared y prime equals 5 minus 2xy squared. And now we have one more step. Divide both sides by the 2x squared y. All right, and now I think this is the last example. That's a direct, straight, implicit differentiation. We have a function of x, or we have x squared. We have a y function, so y squared equals xy plus 5x to the power of 3. What are you going to miss? If you're going to miss anything, you're going to miss the product rule. Product rule. Oh yeah, there's another product rule here. X times y. That's 2 functions. Well, I'll call them 2 functions, even though x is a variable. It's 2 things multiplied together that require a product rule. A and B. A is equal to x. B is equal to y. A prime, the derivative of 1 times x is 1. What's B prime? There's a few ways you can think about this. If I ask you what is the derivative of f, you'd say, hopefully tell me f prime. If I ask you what is the derivative of w, you'd hopefully say w prime. What's the derivative of y? Y prime. That's one way to think about it. Here's a second way to think about it. And that way that I just described is because y is a function. The second way to think about it is, what is the derivative of y to the power of 1? Knowing that we have to use a chain rule. The 1's going to come down, and we'll have y to the power of 0, since we subtract 1 from the power, multiplied by y prime, which is 1 times y prime, which is just y prime. So there's 2 ways to think about it. So we'll plug that in for our product rule. We'll take the derivative of both sides using that information. So the derivative of x squared is 2x, derivative of y squared is 2y, y prime equals ab prime plus ba prime plus the derivative of 5x to the power of 3, which is 15x squared. Now I'll plug in the a prime, b prime. So 2x plus 2y, y prime is equal to xy prime plus y. Since a prime is 1, y times 1 is just y, plus 15x to the power of 2. All right, and we're not done yet. We have to do all the rearranging. I'm going to subtract xy prime from both sides to move it over to the left where its y prime brother is, or sister, or cousin. And then the 2x, it doesn't contain y prime, it's got to go over to the right. So 2y, y prime minus xy prime equals y plus 15x squared minus 2x. I don't hear a toddler. This is usually bad. I just heard him. It's bad news. He's doing something bad, eating toothpaste. Okay, y prime. I'm going to factor that out. I have 2y minus x equals y plus 15x squared minus 2x. Next step, I'm going to divide both sides by that bracket. Y prime is equal to y plus 15x squared minus 2x divided by 2y minus x. That was pretty nasty. We had a stealthy chain rule called implicit differentiation. We had a stealthy product rule, which was x times y. And then we had y's in different spots. We had to rearrange things, collect They're not collect-like terms. We had to common factor y prime, do division. There's lots of things that can go wrong. There's lots of steps. This is not easy. The good part, despite it not being easy, is that it is at least formulaic. It's like a recipe. You can follow a recipe, you can follow a process. You don't have to be very inventive. You just have to be careful. You have to be careful not to miss anything. We'll take a pause here. I just realized this video has gone on 30 minutes because I got excited, and we'll pick up on the last little bit of this section in another video.